Okay, next section, energy. So, scientists talk about energy a little bit differently than we talk about energy in our everyday lives. We need to define what is energy. So, in science, we define energy as the capacity to do work, which leads to the next question, what is work, right? And again, this is very different. You're not going to work. Work is defined as the action of a force through a distance. So in this picture, this man is pushing this box to a new location. That is work. Because he applied a force, he pushed on the box, and he moved it through space. Now, did he necessarily get paid for that? No, that's probably not his job, but that's what work is in science, okay? So energy is the capacity to do work. There are different kinds of energy. So the two big broad categories are kinetic energy and potential energy, and the others we can put in one of those two groups. So kinetic energy, the word kinetic has to do with motion. So this is the energy associated with the motion of an object. Potential energy is associated either with the position of the object or with its composition. So in this example here, we have this 10 kilogram weight sitting precariously on top of a building. Doesn't look very safe. This has a lot of potential energy because if you move it a little bit, it's going to fall, right? As it falls and gets closer to the ground, its potential energy decreases. Where does the energy go? It goes into, it's transformed into kinetic energy as the weight moves faster and faster until it crashes at the bottom. So potential energy can be turned into kinetic energy and vice versa. And what happens to the energy when it hits the sidewalk? This is one that is hard to detect just with our physical senses. But when that weight hits the sidewalk, it causes the particles in the cement to vibrate kind of violently, right? And that motion is related to temperature. And so this goes into a form of kinetic energy called thermal energy. So thermal energy is associated with the temperature of an object. It is a kind of kinetic energy. As we talked about how in a solid state, the particles do move, but it's more like vibrating or wiggling, right? So if the particles are vibrating a lot, so imagine it's, I've gone 10 minutes over lecture and you have to use the restroom really bad. What are you doing in your chair? You're like, come on. You're antsy, right? So the whole class of students wiggling around in their chairs like that is a higher temperature of the object. So when you heat something up, that's what's happening, is that the particles are vibrating more. That's thermal energy. It's a kind of kinetic energy. Any questions about that? You guys are all chill right now.
We have a lot of potential energy.
So the total energy that anything has is the sum of its kinetic energy and its potential energy. And so here's another law. This is similar to the law of conservation of mass, the law of conservation of energy. Energy is neither created nor destroyed. So energy can change from one form to another. It can go from potential to kinetic. Energy can flow from one object to another, but the total quantity of energy is constant. What we observe is that objects with high potential energy tend to be unstable. Think of that 10 kilogram weight sitting on top of the building. It's hanging over the edge. You just give it a little nudge, it's going to fall, right? Well, chemical potential energy, these things are also somewhat unstable. The chemical potential energy comes from the different electrostatic forces between the charged particles that make up atoms and molecules. So positive and negative charges, positive and positive are repelled, negative and negative are repelled, positive and negative are attracted. And there's lots of charged particles, protons and electrons, inside the atoms and molecules, and it's the relationships, the forces that are happening between those charged particles that cause something to have a high chemical potential energy. Gasoline and dynamite have high chemical potential energy, and they are unstable, right? If you give them a spark, they will burn or explode. And that converts their chemical potential energy into most likely kinetic energy of whatever they're blowing up. So energy is always conserved in a chemical or physical change. That's a qualification there, because in nuclear changes, energy is not conserved. But we're not going to do that in Chem 1A. Okay? Energy is always conserved in a chemical or physical change. It can neither be created nor destroyed. So if the energy if it looks like you lost energy, well, you just don't know where it went, right? It didn't cease to exist. We just need to figure out where it went. So systems with high potential energy tend to change in a way that lowers their potential energy. And when their potential energy goes down, where does that energy go? It gets released into the surroundings. So here's an example of a gasoline-powered car. We've got gasoline in the gas tank, and those molecules are unstable. They go through the engine and are subjected to a little spark from the spark plugs, and then they have these little miniature explosions. So that causes different things, pistons and stuff inside the engine to move, which translates into the tires moving and the whole car moving. And what comes out in the exhaust are the chemical products of the combustion of the gasoline. But these are much lower in potential energy, and they're more stable. They're things like carbon dioxide and water. Some of the energy that was lost by the gasoline gets harnessed to do the work, and the car moves forward. But some of the energy is lost to usefulness. It doesn't go into moving the car. It just makes the engine hot, right? So some of the energy from the gas moves the car, but some of it makes the engine hot. So you're not getting as much energy usefully out of the gasoline as you might hope.
Most of it makes it hot. I think gasoline's like 0.0001% efficient or something like that.
I don't know the efficiency off the top of my head.
Well, most of it's good.
Any questions?